you can better introduce your friends.
Okay, thank you. Good afternoon, everyone. I'm the prosy presenter of this paper, Exogenous and Endogenous Data Augmentation for Low-Resource Complex Named Entity Recognition. The first author, Xinghua Zhang, cannot come in person for the visa issue. We are from Institute of Information Engineering, Chinese Academy of Sciences. It's my pleasure to give this presentation. Named entity recognition is to detect the entity mentioned in the test and assign it with a predefined category. For example, location and group. Entities often carry key information in the nest benefiting knowledge acquisition, information retrieval, and so forth. Complex entities which are collected from search queries and take the form of any linguistic constitute such as imperative clause. For example, movie dial M for mother pose challenges for NER systems. Complex NER plays a vital role in advancing the application of NER tasks, and low-resource settings further extend its applicability to a broader spectrum of scenarios. Meanwhile, data augmentation has been shown to be a promising way for low-resource scenarios. Prior studies explore data augmentation for NER, which can be broadly classified into two types: substitution-based and language model-based methods. However, existing data augmentation methods for complex NER encounter limitations in two critical aspects. The first one, limited diversity of augmented data. The augmented data derived from the low-resource training corpus, while entity replacement or language model generation, and then poses the similar entity context patterns with original low-resource data, which leads to the poor data augmentation diversity. The second one is limited quantity of augmented data. Current methods can explicitly generate as much text as possible, but may be computationally intensive and suffer from context entity mismatch issue or incoherent augmentations. Excessive augmented data greatly increase the risk of introducing text noise. This also leads to only a limited amount of augmented data being utilized due to lower data augmentation quality. To this end, we developed the exogenous and endogenous data augmentation method, E²DA, for low-resource complex NER, built upon vector decomposition-based task disentanglement framework, which explicitly generates more diverse textual data and implicitly searches for diverse semantic directions. Our method, E²DA, continuously expands the original low-resource training data will as anchor, and then explores the vast semantic space surrounding each sample. It mainly consists of three parts: vector decomposition, base task disentanglement, provides the task-specific representations for each sample. Exogenous augmentation generates diverse texture data relying on powerful instruction-following ability of large language models. And endogenous augmentation explores the broad semantic space across meaningful semantic directions for utilizing almost infinite semantic features. Complex entities like movie names are syntactically ambiguous and linguistically complex, such as infinitives. For example, to kill a mockingbird. In low-resource situations, the challenge intensifies. Therefore, we first propose a basic entity recognizer for reducing the difficulty of task learning while vector decomposition-based task disentanglement. The vector decomposition, which breaks one vector into two or more components, is similar in spirit to disentanglement. Thus, we explore the vector disentanglement for obtaining task-specific representations, and then perform data augmentations in subtasks respectively. Exogenous data augmentation aims to continuously expand the original low-resource anchor training data, different from substitution of entities of the same type and new task construction based on traditional pre-trained language models. of the Shiyao large language models, LLMs, can generate more fluent and diverse data with tailor-designed instructions, elevating the low quality and increasing the diversity of the augmented data without extra retraining. We query a large language model to generate highly dissimilar data from the original corpus in terms of entity mention and context, and develop the self-reflection strategy to recheck the generated data of LLM, such as the correctness of labels and the diversity of text, to further improve the quality of the generated data. Prior work have confirmed that there exist many semantic directions in the deep feature space. Moving a data sample along these directions changes its features to match another sample of the same class, but with different semantics. Therefore, in two subtasks, we can respectively obtain rich semantic features by searching for such semantic directions on task-specific representations and then effectively augment the training data. However, it is not a trivial work to look for such semantic directions. To capture the meaningful semantic directions, we estimate the covariance matrix for each class to model the intra-class semantic variations. Following this, the semantic features from different directions are sampled based on a normal distribution with the features of training samples as the mean and the estimated matrix at the covariance. If we sample m times, the cross-entropy loss can be formalized as Lm. When m approaches infinity, it can be transformed into the mathematic expectation form. But this expectation form is difficult to program and implement. According to Jensen's inequality and a moment generating function, we derive an upper bound of the loss function to utilize almost infinite semantic features in diverse directions by directly minimizing the upper bound. Under low resource scenarios, the amount of data for each class is limited, which may impair the estimate of covariance matrix. Therefore, we further explicitly take entity mention and its context into account for capturing more precise intra-class semantic variations. According to the property of multiple random variables in the moment generating function, we can further strengthen the upper bound of endogenous augmentations with entity mention and context for each entity token. Considering the data quality generated by the large language model, we first train the model on the exogenous augmentation corpus and then fine-tune it on the original low-resource training data. During prediction, combining results of two subtasks gets the final NER result. The datasets are collected from Bing search queries, questions, and wiki sentences. It consists of 10 sub-datasets and 6 entity types. We perform the low-resource complex NER experiments on 4 settings. That is, the number of training data is respectively 100, 200, 500, and 1000. It's worth noting that the number of data in test set is large, which can better testify the effectiveness and generation of the methods. We can see that our data augmentation method, E²DA, achieves the notable improvements under 4 low-resource scenarios. Overall, the performance of nearly all methods tends to progressively improve as the quantity of training data increases from 100 to 1000. Our method has more obvious advantages under the lower resource settings due to the sufficient augmentations based on almost infinite semantic features and more diversified generated data in the task disentanglement framework. By ablation study, we verify the effect of each component and confirm their effectiveness. By comparing the last 2 rows, we observe that low-quality augmentations are more likely to have a negative impact under the higher resource settings. To explore the impact of exogenous augmentation during training process, we show that the best F1 scores on datasets with 100 training as the training process goes. Our method with and without exogenous augmentation are respectively described with solid and dashed lines. We also mark the best F1 score throughout the entire training process with star and triangle for each dataset. We can observe that exogenous augmentation speeds the convergence of the model, where it achieves higher performance in the early stages and attains optimal performance at the fastest speed with the support of the exogenous augmentations. To explore the impacts of exogenous augmentation during training process, we also depict the training curves of F1 scores on datasets during training when the number of training samples is 100. We can observe that the NER model with endogenous augmentations achieves the better performance and holds more stable learning process under the low resource setting. In addition, the NER model without endogenous augmentations has caused the overfitting problem due to the less training data. Endogenous augmentations have elevated the overfitting issue because it searches for the diverse semantic directions and utilizes more meaningful semantic features surrounding the low resource samples. To analyze the contributions of exogenous and endogenous data augmentation to performance gains, we respectively give the test F1 scores of using only endogenous data augmentation and further introducing exogenous data augmentation under 4 low resource settings. Only endogenous data augmentation method has achieved optimal results on almost all datasets. It's worth noting that our endogenous data augmentation method does not require any additional explicit test data and only explores a small amount of data samples in the implicit semantic space by minimizing the upper bound of the desired loss, which is more effective and efficient. Furthermore, we introduce the exogenous data augmentation and the F1 score further increases under 4 low resource settings. Lastly, we perform the diversity analysis of the generated data in exogenous data augmentation. Through qualitative analysis, self-reflection strategy enhances the diversity and utility of the generated data in the finite number of augmentations. Through the quantitative experiments, our method generates more than 90% of new entities and the highest percentage of contextual non-entity words. Overall, we propose the exogenous and endogenous data augmentation method E²DA. The exogenous augmentation expands the original low resource data by introducing more diverse new data. The endogenous augmentation sufficiently explores the meaningful semantic directions and explores the infinite semantic features. 2 complementary data augmentations enhance the low resource data in terms of the local semantic and global test space. Please feel free to send the emails to the first author. That's all. Thank you.
So thanks.